Okay, everyone. So I'll just kind of give you a warning. There's probably going to be some background noise just because my husband's cooking dinner. So if you hear the sink running or chopping or something, that's what that is. Okay, so today we're starting Chapter 7. And Chapter 7 is all about what's called electrochemistry. So those of you who may be going in the engineering route will probably have some sort of electrochemical course you're going to be taking. If you're going more the biomedical, maybe not so much, but you know, grade 12 is all about kind of hitting your general chemistry for all disciplines of science that you may be going into. So electrochemistry is the process of involving obviously chemical reactions, and this is where chemical energy is converted into electrical energy. Okay, so essentially what we're doing is inside, if you want to think of, for example, inside of a battery, right, an electrochemical cell, you have a chemical reaction that's happening. Electrons are gained and lost in that process, and then we can use those electrons to do work for us, let's say in a circuit. There are a lot of natural biological redox reactions that you may have already covered. For example, photosynthesis, or anything where something is reduced and something is oxidized. That's what that's all about. And then you have corrosion or rusting, which is very common. Okay, so a redox reaction is actually two parts. So you have oxidation and reduction. So the term redox is really reduction, oxidation in one. So you have both processes happening. Electrons are essentially transferred in this. So you will get to this, but Leo the lion says GER is a way of remembering which process is which. So oxidation is where you have a loss of electrons, or losing electrons is oxidation. And then GER is for reduction. So gaining electrons is reduction. So what ends up happening is something is losing electrons, so losing, and of course they have to go somewhere to the substance that is gaining. So you have, of course, both processes, the reduction and the oxidation. So what we're going to look at first is how to assign something called an oxidation number. Okay, so an element's oxidation number is referred to as either the real charge, so of course if you have an ion, it's going to be a real charge, or what's called an apparent charge. So this would be like the assigning of a charge as if you were to give it one, even though something may not have ions to begin with. So you can have a molecular compound and still assign it oxidation numbers. Okay, so there are many rules that kind of go with this. You kind of just basically have to know them and get comfortable with them. There are different things online that you can use to help you determine oxidation number possibilities, but some elements can vary very greatly. Okay, so let's take a look at the rules for assigning oxidation numbers. And yes, before anyone asks me, you do need to know these, right? So it's not a matter of like memorizing them. It's a matter of being able to apply them, right? So over time, if you practice this enough, you kind of get to know them by just doing it, right? So for example, number one, we're going to go through each one. So atoms that are in their elemental form is always assigned a value of 0. So for example, if I had sodium metal, right, I would assign that as 0. If I had hydrogen gas, right, that's the elemental form, I would assign that as 0. Anything that is how it will naturally appear in its element form. So that includes the diatomics, right? So as they come in pairs, naturally they're going to be 0. Okay, number 2, monatomic ions. So ions of only one atom. Your oxidation number is whatever the ion charge is. So for example, if I have a sodium ion, okay, my oxidation number is +1. If I have a nitrogen ion, right, nitrogen gains 3 electrons, my oxidation number is -3. So if you have a single element that is an ion on its own, then the charge is the same thing as the oxidation number, right? So it's the real charge. Okay, number 3, oxygen. So oxygen is always assigned an oxidation number of -2, okay, but there are 2 exceptions. In a peroxide polyatomic, so peroxide polyatomic looks like this. It's an O2 polyatomic that has a -2 charge. So in this case, each oxygen is assigned a -1. Okay, this should make sense. If there's 2 of them, and the whole thing adds up to -2, they should each be -1, right? -1 gives us -2. The other case would be if you have oxygen that is in OF2. And I have a note here saying that this is a typo. Yes, this is a typo. So in OF, it should be +2. Okay, hold on. So let me just explain that, right? OF2. So fluorine, when fluorine is an ion, it has a charge of -1. So if there are 2 fluorines, that's -2. But OF2 is neutral. So what that means is all of these atoms must add up to a 0 charge. So in this case, oxygen would have to be +2. Okay, so yeah, that is definitely a typo there. So please make that correction. I believe in your textbook, they should have already corrected it, but in my teacher version, it was still in error. Okay, number 4, hydrogen is always assigned a oxidation number of +1. Of course, number 3 and 4, we're not talking about the elemental form, right? So oxygen in the elemental form is still assigned 0. Hydrogen in the elemental form is still assigned 0. We're talking about when oxygen and hydrogen are in molecules, okay? So when hydrogen is in a molecule, it is always +1, except with hydrides, metal hydrides. So a metal hydride is anything that has, so a metal hydride is where you have a metal with hydrogen. Okay, so for example, magnesium hydride. They're not really seen very often. Hydrogen can behave like a metal or a non-metal because it has +1, -1 options, but when it's paired with a metal, it's always going to be -1. Okay? All right. So let's take a look at the next ones. I need a little bit more space. I'm just going to make, just give me a second here. I'm going to copy this over. Do a new sheet. Yeah. Okay. So, okay, number 5. Oxidation numbers in compounds must add up to a sum of 0. Okay, so what does that mean for us? So that means if you have a molecule, such as water or anything, if it does not have a charge in the corner, okay, so what I mean by that is it's not a polyatomic, right? Like carbonate has a charge in the top right-hand corner. If there's nothing written there, you know it has to have a sum of 0. So when you're assigning your oxidation numbers, it has to match that, obviously following all the rules we just finished saying. So oxygen is always -2 unless it's in peroxide or OF2, which is not. And hydrogen is always +1 unless it is in a metal hydride, which it's not. So let's check this out. So if we have -2, and then we have 2 +1s, which gives us +2, those 2 things add up to 0. So that's correct. Okay. Let's say we had something like, let's do, for example, okay, nitrogen dioxide. Okay, so nitrogen dioxide, oxygen is -2. It is not any exception, right? There are 2 of them, so that's -4. So actually, to figure out what this nitrogen is, you know it has to be positive 4 because it has to have a sum of 0. Okay? So by using the rules that you know already, you'll always be able to figure out what the unknown element is. Okay, number 6, oxidation numbers in polyatomic ions must sum to the ion charge. Okay, so what that means is if you have a polyatomic ion, instead of all of the element numbers adding up to 0, they have to add up to -2 in this case. Or if I have ammonium, right, they have to add up to +1. So you still go about assigning the oxidation rule. So oxygen is -2, right? This is not an exception. There are 3 of them, so that's -6. So carbon has to be +4 in this case because I know +4 and -6 gives me -2. Okay. Now, it's important to understand that when you are assigning numbers, right, you literally only assign it per element. So even though there are 3 oxygens, and you know how I did this work to make it -6, so even though there are 3 oxygens, when I ask for the assigned numbers, you only would tell me -2. This -6 business is just so if I can get help to figure out what carbon is. Okay, but in terms of the actual value you're assigning, it's per one of those elements. Right, so for nitrogen, if we take a look here, ammonium, we have NH4 +1. So hydrogen is +1. There are 4 of them. So that means nitrogen has to be -3 because this would be +4 and -3, which adds up to +1. Okay. Now, if you have an ionic compound that has a polyatomic ion in it, let's say something like this, potassium dichromate. Okay. The easiest way would be to think of this as the separate ions. Okay, so really this is potassium and dichromate. Okay, so this will help you when you're assigning numbers. So for example, right, I know I'm gonna have to assign a number for each of these, potassium, chromium, and oxygen. But potassium is just a regular ion with a single charge. So I know potassium is +1. So this is just chromate. So chromate, oxygen is going to be -2, right? There are 4 of them, so that's -8. So when you're thinking about how this has to add up to -2, we know that chromium would be +6. Okay. Altogether, that compound is going to add up to 0, but I find it's easier to assign the oxidation numbers by thinking them as their individual ions. Okay. Now, number 7 says, always assign the more electronegative element a negative oxidation number. Okay, so there's going to be cases where maybe you have multiple options. To be honest, if you follow all of the other rules we talked about, you should never have a problem with number 7. Number 7 will basically take care of itself. You'll already be doing that. And then, of course, this is number 8. In a compound or ion containing more than 2 elements, the element written furthest to the right takes the most common oxidation number. Okay, so at the back of your book, you don't really have information on oxidation numbers. Let me just confirm this guy. I don't believe you do. No, you don't. Okay, but when you're looking at this, so in a when there's 2 or more elements, the element written furthest to the right takes the most common oxidation number. Maybe we'll come across a specific example that this will apply to, because to be honest, you're already going to naturally be doing this. I don't think I ever recall having to go through these last 2 specific rules. They're kind of something you're already doing. But anyways, let's look ahead to the next section and then we'll do some practice problems.